Hello, everyone. Welcome back. We're starting chapter 26 today. And as much as I dislike the material from chapter 24, um, chapter 26 is probably my favorite of all the materials in this course, mainly because I have a background in materials science, and this chapter covers a lot of those materials properties as they result, or excuse me, as they refer to resistivity and resistance in materials. So we're going to be talking about that in this chapter. We're also going to be introducing the idea of electric current in this chapter. We have not yet actually had the need to describe the motion of charge, not because we haven't had charges that are moving in a system, but they weren't necessarily self-contained within material that can transport them from one location to another. And so current is going to be the charge that passes through a given conducting material. And the the easiest way to probably define current is just to use the mathematical version of the definition, which is a change in charge with respect to time. And on the infinitesimal level, this would give us an instantaneous current. And we're not going to use C to represent current because we're already using C for capacitance. We're also using C for the unit of charge, which is the coulomb. And so we're going to use lowercase I to denote the current. We can take that same expression and we can increase the time interval. So delta t is typically considered a large time interval, at least something that's larger than 0. And if that's the case, for large time intervals, there are things that can change along the way. And so the best that we can hope for in that case would be an average current value. So what are we going to do with that? Well, the current, or the rate at which our charge is going to move through any given material, is going to depend on the structure and the properties of that material. And so what we're going to do is we're going to draw a wire, so a very, very thick wire here. And this wire is made of a conducting material, and we know from the first chapter in this semester that conducting materials allow for free charge motion. And if you go back in your notes, I'm pretty sure I had the word free in quotations because it's not 100% free motion. There's going to be a little bit of hindrance to the motion of that charge, and that hindrance is what we call resistance. So we will be denoting resistance with capital R, but there is another term that we're going to see called resistivity. And the two sound very similar. They both have the root word of resist. But resistivity, we're going to use the Greek letter rho. And what the resistivity does is it is an intrinsic property of the material. determines the resistance? Maybe I don't want to use the word conductor necessarily because we can have insulators that have very, very, very high resistance, and they prevent the charge from moving through. So we'll say the resistance of the object. So resistance, R, is the let's see how I want to word this. I want to use the word resistance, but that would be a circular definition. Well, for right now, I'll just use that for lack of a better term. Well, let's do this. We'll say resistance is the ability of the object to resist charge flow. And that term right there, charge flow, that's going to basically mean our electric current. So as our charge moves through this material, the resistance is the ability to resist that charge flow. But the resistivity is a characteristic or a property of the material that we are using, and that contributes to the value of the resistance. And so we're just gonna jump in and talk about why we have resistance, resistivity, how it affects current. And to do that, we're going to zoom in on our wire. And to have any kind of electric charge moving through this wire, at the moment, this conducting material, whatever it is, it already has charge in it. And we say that that charge is a null charge. And so the net charge within the conducting material is 0. But that just means that we have equal amounts of positive and negative charges bouncing around inside the material at random directions. And so if I have these charges bouncing around in random directions and I try to measure the flow of that charge, well, that random action of charge moving around is just going to result in the net flow of charge equaling 0. And that will continue to happen until we give these charges a reason to start moving in one direction or the other. And that reason will be when we connect the ends of our conducting material to some kind of electric potential, like a battery. And so now I'm going to break this down to just positive charges. So now we have, for the sake of our discussion here, we have some positive charges that are randomly bouncing around inside our material, but now we have a positive negative potential, which is going to result in a positive charge source entering from the left, and that positive charge source is going to be attracted to the negative charge source on the right. And so we're going to see these charges that are inside the conducting material, they're going to start moving towards the right because they're being repelled by the incoming positive charge, and they're being attracted by the negative charge on the other end. And now that we have all of these charges moving together in the same direction, we have accomplished this rate of change for the charge as it moves through our material. But as these charges try to move, I didn't want to go back that far. As these charges try to move through the material, remember that these electric charges, they're particles, and these particles have to navigate a gauntlet of atoms within the material itself. A lot of these materials will have, oops, got too close to the bottom of the screen there. So a lot of these materials will have a periodic, almost lattice type of structure, and so everywhere where I've drawn an intersection would be an atom of the material that is making up this conducting wire. So all of these atoms, they have chemical bonds that are connecting them together as part of this lattice. And even though most matter is considered to be empty space, if we look at the model of an atom, you've got a very, very small nucleus, which is then surrounded by some electron orbitals. But even though there's a lot of empty space within that atom, that electron orbital is fairly large in consideration. And so every one of these atoms has a large electron orbital, which is going to, in turn, affect the motion of any charge that is trying to move through this material. So as our charges try to move through the material, and we will have some new charges that enter the conductor from our potential source. As they do this, they kind of end up going through this gauntlet of being pushed around by all the different atoms and electron orbitals that are surrounding them. And this causes the charges to take more time to get through the object itself. And so we call this overall effect of hindering the motion of the charge resistance. And the structure of the material, the way that I have this lattice drawn out, this would be unique for every kind of material or composite material that is out there. Now, when you think of a wire and a material that you would use for a wire, most people would probably use copper, but copper is not necessarily the best conductor that is out there. Gold is a better conductor than copper. Silver is actually an even better conductor than gold, but for some reason we keep using copper in so many of our electronics, and it's not as efficient. And that's because copper has a greater gauntlet, so to speak. The way that the copper the copper atoms are laid out within the lattice work causes the charges to have more resistance. Yet gold and silver don't introduce as much resistance to the flow of charge. But these are just far too expensive in terms of the fiscal benefits of having a good conducting material. And so the resistivity, this rho term here, this is the measure of the material property that causes this hindrance as our charge moves through the material. So copper will have a resistivity value that is unique to copper. Gold will have a resistivity that is unique to gold. Silver will have a resistivity that is unique to silver. And so if I were to construct 3 wires of the same dimensions, the copper wire would actually have the highest resistance of all of them because of the way that the copper atoms are aligned throughout the material. And silver would actually have the lowest resistance of all the materials because of the way that the silver is distributed throughout that material. Now you'll notice that I said that each of these wires are of the same size and same shape. And that's an important distinction, because now what we need to do is we need to consider what happens to the resistance if we have wires of different shapes. So different length, different thickness. Does that affect anything? And right now the value of our resistance is going to be proportional to the resistivity. So the higher the resistivity, the more hindrance our charge runs into, the higher the overall resistance. But there's more to this equation. We need to turn this into an equality and not just a proportionality. So let's take the same idea of our charge running into some hindrance as it goes through this material, and let's consider some different scenarios. Let's try a very thin long wire and a short, well, actually let's do one thing at a time. Let's do a thin long wire and a wide long wire. So we've got the length of each of these wires is the same. We'll say that each of these wires is made of the same material. So each wire has the same resistivity. It has the same unique distribution of atoms throughout. And I'll just go ahead and draw a couple of lattices here. And obviously for the small thin one, we're not going to have as many there. And let's consider that you have a charge that you want to move through these 2 wires. Now with the first one, the corridor that this charge gets to move through is pretty thin. And as it moves through, it's it's going to be bouncing around as it goes through. And so there's a certain hindrance involved. As the other charge goes through, it's definitely got more room to bounce around, but is that going to affect the overall rate of flow for the charge? And right now, it may not look like it, at least not for an individual charge, but we need to consider the fact that there are going to be multiple charges that are lined up waiting to get through this wire. And now we have kind of a bottleneck scenario with the thin wire, because the corridor of the wire is only so wide. We can only allow so many charges to get through. Whereas for the thick wire, the corridor is very wide, and we can have multiple charges entering the wire, and then each charge is going to bounce around as it goes. And most of these charges are probably not going to interact with each other, but even if they do, eventually they're going to find their way out the other side. But for the thin wire, we can only have so many charges make their way through that very thin corridor. And this idea is similar to like a concert venue. If you've ever been to a concert at a convention center, come on, change color. There we go. And the concert's over, and so everybody has to leave. Well, at that concert venue, if you look around, how many doors are there at the concert venue? And you say, well, there's lots of them. And so lots and lots and lots of doors means that you can get lots of people to exit the building all at once. And this is also a fire code issue. You have to be able to evacuate a lot of people all at once versus, if you only had one door and you were trying to get 60,000 people out of the building, it's probably going to take you quite a while, because now everybody has to line up to get out of the door, versus having multiple doors, or in this case, a very wide cross-sectional area to exit, means that you can get more people through. And getting more people through means a higher flow of individuals. In the case of the wire, having a larger cross-section means getting a higher number of individual charges through the wire at any given time. And so the current for the wide wire is going to be higher than the current for the thin wire. Up at our definition, we said that resistance is the ability of the object to resist the flow of charge. Well, we've got the current for the wide wire, we've got the current for the thin wire, and we said that the current for the wide wire was going to be quite a bit larger than the current of the thin wire. But that's because the resistance of the thin wire is so much larger than the resistance of the wide wire. And we can see why that is now, because the cross-section of the wide wire is so much larger than the cross-sectional area of the thin wire. And what this means for us is that if the area is very small, the resistance becomes very high. If the area is very high, we're talking about the cross-sectional area that our charges are passing through, then the resistance is low. And this is an inverse relationship. There's an inverse relationship to the cross-sectional area and our resistance. And so I'm going to pair that with the proportionality that we have for our resistivity. And so our proportionality expression, we're going to combine these. We have a one-to-one relationship with resistivity. We have a 1 over A relationship. But there's one more thing that can cause some resistance values to change. And so the next consideration that we need to make, in this case, we'll keep the cross-sectional area of the wires the same, but we'll make one of the wires much larger than the other. And so we've got charges that are ready to enter each of these wires. Each of these wires is going to be made of the same material, so each wire has the same resistivity value. So we have our lattice of all of our atoms inside, and then our charges need to move through. So here I've drawn some random paths for a single charge that moves through each of these wires. And what do we notice with respect to the length of the two wires? So here we have length of the first wire. This will be the length of the second wire. Well, now consider that you're walking down a hallway with a number of people, and all the people are kind of shifting around, moving. So what are the chances that you walk down that hallway and you bump into someone? And you might think, well, with everybody moving around, there's probably a pretty good chance that you're going to bump into someone. But do you, and that, by the way, bumping into someone would be synonymous with the resistance of a charge moving through the material. But now consider what are the chances that you would bump into someone walking through a very short hallway versus the chance of bumping into someone walking through a very, very long hallway. And because you have all this extra distance that you have to cover, the chance of bumping into someone is going to be much higher. And so as the length of the wire increases, the chance of some kind of interaction or bumping into somebody or having to change your path due to any hindrance means that the resistance is going to go up. And if the wire is shorter, oops, don't know what happened there. If the wire is shorter, then you have less of a chance of running into someone, and so the resistance goes down. And so this is a one-to-one proportionality for the resistance. And we're going to plug that in. And as it turns out, This is the last piece that we need to describe the resistance of our object. It depends on three different characteristics. It depends on what the material is made of. So we have a material property here. It depends on the length of the wire, and it depends on the cross-sectional area of the wire. But we now have our equation for the resistance of any object. And this is kind of interesting because in the last chapter, we had, in the case of the parallel plate capacitor, we had an expression for the capacitance of the capacitor, and this was what I was calling the store-bought equation for the capacitor. And what was it made up of? Well, it was made up of the geometry of the capacitor, cross-sectional area and separation distance, and it was made up of the materials property, epsilon naught. And epsilon naught described the material that was in between the plates, which did not have to be just empty anymore. We could also use some kind of dielectric material in there, but that was materials property. So look at the resistor. Well, how is the resistor defined? It's defined with a materials property and geometry. And so this is what I will refer to as the store-bought value of the resistor. And this means that when you go to an electronics store and you buy a resistor, the rating for that resistor is fixed. It is determined by the material that it was made out of and the dimensions of that resistor. Well, the capacitor had another equation that could be used to measure the capacitance. It was the ratio of charge to potential. So is there a similar equation that can be used to measure the resistance of an object? And there is. That equation is called Ohm's law. And Ohm's law states that when an electric potential is applied to an object, the resistance of that object will determine the current that passes through it. Or, with an algebraic reshuffling, the resistance of an object can be measured as the potential difference across the resistor over the current that passes through that object. And right up here, we said that resistance was the ability of the object to resist the charge flow. And look at what we have. We have a potential source that has been placed across the two sides of our resistive material, and we have charges that are moving from one side of the material to another. By definition, that is current. And so, yeah, Ohm's law is, in fact, telling us what is happening. But the rate at which that current is able to travel through that conducting material is going to depend on what the material is and what the dimensions of the material are. So for capacitors, we had the ratio expression and the store-bought expression. For resistors, we have a ratio expression and we have a store-bought expression. Well, let's talk about units. From the ratio expression, we have potential, which is in volts. And we've not yet talked about the units for current. So let's go back to the top here, where we had our current defined. Current was the change in charge over time. Charge has units of coulombs, time has units of seconds, so current is a coulomb second, but the more common name for that combination is the amp or ampere. So we have units of amps for current. We're going to bring that down to our ratio expression. We have volts over amps. But there is a more common name for the unit of resistance, and that is an ohm. Hence the title of Ohm's law. And an ohm, we don't want to be labeling our resistance with an O, because then that's going to look like a 0. So instead, we're going to use the Greek letter of omega. So omega is the last letter. Kind of looks like a horseshoe. I've had students say horseshoe, and I'm like, no, it's omega. But yeah, it looks like a horseshoe. But ohms or omega will be the units for resistance. And so now that we know that, let's bring that over and figure out what the units of resistivity need to be. Since our resistance is already in ohms, we'll put ohms there. Resistivity, we need to find the units for that. Length is in meters. Cross-sectional area is in meters squared. And so we're actually going to lose a couple of those meters. And so all that's left to figure out what the units of resistivity need to be. On the left I have ohms, on the right I don't have any ohms, so I'll put those in there. But then ohms is the only thing I need. I don't need these meters down in the denominator, so I'll insert some meters into the numerator, and now everything is working out proper. The units of our resistivity are ohm meters. Now, there are definitely some advantages to playing around with the units in a system. A lot of times, just by shuffling the units around or converting the units, you can produce another equation for that system. But this is one case where we would actually get ourselves in trouble if we tried that. Because if you look at the units here, well, what do we measure with ohms? Well, we measure resistance. What do you measure with meters? Well, we measure length. Oh, okay, so I guess resistivity is resistance times length. Well, no, it's not. If you try to compare that to that equation, well, rearrange that top equation for resistivity and show me what you get. Well, resistivity would be resistance times area over length. And, well, those are not the same thing. And we're going to get ourselves in trouble if we try to use that. The problem here is that our cross-sectional area and our length have the same units of meters, and we lost some of that information as we were combining the units. And so we have to be careful in how we shift back and forth between these two. But there's nothing wrong with these two expressions. But it is worth noting that the resistance of your object is dependent on these three values. The resistance of your wire depends on what you make the wire out of, how long the wire is, and how wide the wire is. Resistivity does not depend on the resistance of the object. Okay? We can solve for the resistivity, but the resistivity is not defined by any of this. The resistivity is a fixed property of the material. Now the book takes about a paragraph on this next topic, which is called conductivity. And conductivity is really just the antithesis of resistivity. So resistivity, up above, our definition of resistivity said that this was an intrinsic property of the material that determines the resistance of the object. So the resistivity plays into how much resistance we're going to have. Well, the conductivity is just the opposite. The conductivity is going to be an intrinsic property of the material that tells us how that material will allow charge flow. And it's a pretty straightforward relationship. If resistivity measures how much we resist the flow of charge, and conductivity measures how much we allow the flow of charge, well, these two are just going to be inverse values of one another. And so conductivity, we're going to use sigma, and the relationship between the two is just an inverse. So the higher the resistivity of a material, the lower the conductivity. And that should make sense. If our material is resisting the flow of charge, then we can't conduct very much charge. And if the resistivity of the material is very low, then we should be able to conduct a lot of charge, so we would have a high conductivity. Since we now know the units for resistivity, what would the units of conductivity be? Well, here we have 1 over ohm meters, and so that would be the units of our conductivity. You could also write that as inverse, but I've never really been comfortable using negatives for my units. I just prefer to either keep them in the numerator or the denominator, respectively. All right, so what should we talk about next? Well, let's try a problem. Let's put this material together into a problem. We have a copper wire. So copper wire, it has a length of 2 meters and a radius of 0.5 millimeters. So we could assume this to be like an extension cord. And what I want to know is, what is the resistance of this extension cord? All right, so we have a radius, we have a length. Now the radius of that wire, I should probably use the same notation there. So the radius of the wire implies that the wire is or has a circular cross section. And so the cross-sectional area would be pi r squared. We should do ourselves a favor and convert that to meters before we go any further. We have half of a millimeter, so 0.5, and then we have to divide that by 1,000 to get to meters. So we have 0.0005. And that is going to have to go into that expression. So we have pi of 0.0005 squared. And this is just going to get smaller. And we need to multiply by pi, which gives 7.85, 10 to the -7 meters squared. So a very, very, very small cross-sectional area. And based on what we know about resistance is that if we have a very, very, very small cross-sectional area, that's going to result in a high resistance value. We have our length of 2 meters, so that's going to go in there. So all we're missing is the resistivity. We were told that this was made out of copper. So what we need to do is either in the electronic text or in the read study practice section of Wiley Plus, or you can just go online and you can Google it. We need to get the resistivity of copper. I'm just going to go ahead and Google it. Resistivity of copper. And Google is telling me that the resistivity of copper is 0.0171. Let's see here. Well, this gave this in some weird units. Let me try a different source here. Let's see. We've got, oh, there's a, that looks like a better source. Here we go. Table of resistivity values. That will be more helpful. Google gave me some weird ohm millimeter per meter thing that wasn't being very helpful. But copper, now obviously there's going to be different copper composites. You can have just, plain elemental copper. It could be annealed. It could be mixed with zinc. You could have a some kind of a bronze compound that's going to change the resistivity. And so you need to be absolutely sure as to what value you're looking up. This one just says copper. So I'm going to assume that this is elemental copper. Oops. It's 10 to the -8 ohm meters. All right. So all these numbers are going to have to go in to our resistance expression. We have 10 to the -8. We have 2 meters. And we had a cross-sectional area, 7.85, 10 to the -7. Now, do yourself a favor. Take care of your 10 base there. You have 10 to the minus 8 divided by 10 to the minus 7. That's going to result in a 10 to the minus 1. And then all you have to do at that point is multiply your coefficients together, which is 1.68 times 2 divided by 7.85 makes for 0.428 times 10 to the minus 1, or 0.0428, or 4.28 10 to the minus 2 ohms. All right, so we got everything correct. Looks like it. So in terms of our measurements here, we have, let's see, this would be about 42.8 milliohms for the resistance of that extension cord that we're talking about. And so that doesn't really seem like much, but for an extension cord, you don't want a whole lot of resistance, because one of the effects of resistance as your charges are bouncing around inside these wires. So if we look at one of these case scenarios here, every time our charge bounces around, there's going to be a little bit of contact, there's going to be a little bit of friction, and there's going to be a slight increase in the thermal energy of that material. And so the material is going to warm up as these charges are passing through them. And the higher the resistance value of the material, the greater the temperature increase of that object is going to be. And for materials that start generating heat, as we have heat that's being generated inside these materials, if that material can dissipate the heat at a rate that is at least equal to the rate at which the heat is being generated, then it can maintain a constant temperature. It can maintain a constant operating temperature, so to speak. But if the rate at which heat is being generated is much higher than the rate at which the heat can be dissipated, then you run the risk of your material melting. And in the case of electronics, this goes back to the idea of seeing the little blue smoke or smelling the little blue smoke, because at that point you've probably destroyed the object, you've burnt out the resistor. But in the case of, say, an extension cord, what does that mean? Well, the material inside of the cord would be made of copper, but then you would probably have some kind of protective sheathing that goes around the wire. First of all, to prevent you from getting shocked as you handle the wire, but also to prevent any kind of short circuits. But if the wire starts heating up, it needs to dissipate that heat, and where is it going to dissipate it through? Well, it's going to dissipate it through that protective sheathing, and that sheathing is usually made of some kind of polymer composite or a plastic, and that plastic could do one of two things. It could melt, And if the plastic melts, then you've got an exposed section of wire, which can then short circuit, could cause a spark. Another thing that could happen is that as that plastic sheathing melts, it could catch fire. And that fire could then spread to some other area. And a big concern for something like this would be like lights on a Christmas tree, or lights that you put outside on a tree during the holidays. And so if we consider a string of lights and we plug those strings together, one after the other, I'll make a couple of strands of lights here. A lot of the older strands of lights that you would buy would have warnings on them that would say don't connect more than 3 of these in series, which would mean one after the other. So here I'm just putting in some different colors for the different bulbs of the lights. And so effectively what happens when you connect these strands of lights end to end to end? Well, each strand of light is going to have the same cross-sectional area of A, and each strand of light has the same length of L. But when you connect them end to end to end, you are adding 3 times the length to the path that these charges now have to follow. And I really messed that up. So each of these wires probably has copper inside of it, but now you've tripled the length of the path that the charges have to follow, so you've tripled the resistance. And as we know, higher resistance is going to result in a higher generation of thermal energy. And you could end up causing one of the wires to melt, and after that you could have a discharge or fire. And most of these holiday lights end up on a tree, or maybe a conifer bush outside or something. And not only do you now have the wire on fire, but now you've got the tree on fire, and if it's in somebody's home, that's a big problem. So it's important that we follow the safety precautions here. A lot of lights that have been produced today use a parallel wiring system, which we'll talk about series and parallel resistors in the next chapter. But if you can connect the lights in parallel, you actually reduce the amount of resistance. In addition to that, you have holiday lights that are now being produced using LEDs, as opposed to the traditional incandescent bulb, which uses high resistance filaments, and they get very, very hot. And a few years back, I was putting some garden lights outside, and I decided to splurge, and I bought some LED garden lights, which are just basically more expensive versions of the holiday lights, because you're buying them out of season. And I remembered the old warning, don't connect more than 3 of these in series. Well, the LEDs are far more energy efficient, and they just don't produce the same amount of thermal energy as a result. And so I was looking at the safety precautions with these LED lights, and it says warning. Oh, can't even spell today. Warning. Don't connect more than 30 of these in series. And each of these strings of lights were about 15 feet long, and um, I don't think that's going to be a problem. Not only because I just don't have that much room in my backyard to put up, let's see, 30 times 15, that'd be like 450 feet of lights. I don't have that much room. Plus, I don't think I could afford to buy 30 sets of those lights. Those lights were probably like $15-20 per set. So LEDs are really the way to go in terms of not only reducing the amount of energy that you waste due to the generation of heat, but they're going to last way longer. LED bulbs are more expensive, but the return on investment that you get from them, you might spend $15 on a strand of lights like this, but they're going to last you probably 15 to 20 years, whereas an old incandescent strand of lights might last you 3 or 4 years at most. And the same analogy works with light bulbs that you use at home. The old incandescent bulbs might last you 6 months to a year, and they might be pretty cheap, but you're going to go through, you know, probably 20 or 30 of them within a 10-year time span, and compare that to an LED bulb that you can buy, and it'll fit in the same socket, but it'll last you the full 10 years, and in the long run, you end up spending less for that LED, and you're producing way less trash, and you're wasting less electricity to produce the same amount of light, and so you're also saving money on your electric bill. All right, so we'll come back and we'll discuss some more on resistivity and wires and current. And then this chapter is going to segue very well into chapter 27, which is where we will start implementing resistors into circuits. And so we'll basically see the same kind of problems that we had with capacitors, only now we're using resistors. And then at the end of that chapter, we'll combine resistors and capacitors into the same circuits, and we'll see how that affects the math. So we'll see you then.